The title of the talk is Sample Optimal Algorithms for Low-Rank Approximation of Positive Semidefinite, or PSD, and Distance Matrices. Okay, so this is a class of matrices for which you can get significantly faster algorithms for finding a low-rank approximation to them. In fact, the algorithms are so fast, they're sublinear in the size of the matrix. And the hope is that these techniques also apply to other structured families of matrices. So this talk is based on two works, one joint with Cameron Musco and one joint with Anesh Bakshi and Nadia Chepurko. Okay. So what is the low-rank approximation problem? So for the purposes of this talk, we want to output, we're given a matrix A, and we'd like to output a rank K matrix A prime, and we'd like to output A prime in factored form. Okay, so we can write A prime as a tall thin matrix U times a wide fat matrix V. And this is useful for a number of reasons. One is that it provides significant parameter reduction from the original matrix A if this inner dimension K, the rank parameter, is small. Okay, and we'd like A prime to approximate A. And we're going to focus on Frobenius norm in this talk. Remember, Frobenius norm is just the Euclidean norm of the entries of A, of a matrix. So what we'd like is that the Frobenius norm of A minus A prime, well, it might not be the best rank K matrix. A prime might not be the best, but it's at most 1 plus epsilon times the optimal cost of approximating A by any rank K matrix. You can solve this with the singular value decomposition. But for our purposes, that's too slow. And in fact, there are much faster randomized algorithms for this purpose. And they achieve a running time, which is n in z of A, where n in z of A is number of non-zero entries of A, plus what's typically a low-order term, n plus d times poly k over epsilon. Okay, k is the rank parameter, epsilon the accuracy. And so n in z of A could be as large as nd if you have a dense matrix, but even that would be faster than the SVD. I mean, SVD is nd squared time, and for sparse matrices, this is significantly faster, right? This could be order n plus d. So you can do very fast algorithms for general matrices, but maybe this is still not fast enough for you. For example, maybe the matrix A is not stored anywhere. Maybe every time you want to read an entry of a matrix A, you have to do some expensive operation. Perhaps this is a kernel matrix. You have to evaluate a kernel function applied to 2 points and so on. So can you get even faster algorithms? That's our question. And for general matrices, the answer is no. So if you want this relative error guarantee, then there is an n in z of A time lower bound. Basically, you have to read all the non-zero entries of A. Otherwise, sorry, is there a question? Or please stop me if you have any questions. Otherwise, can you find the infinity here, right? I mean, if you don't read all the non-zero entries, you're not going to find this infinity, and that's a problem because the first thing a good low-rank approximation will do would be to subtract off that infinity. So you can't hope to do better than n in z of A time for general matrices. But what about structured matrices? In particular, what if your input matrix is PSD? So let A be a positive semidefinite n by n matrix, so symmetric, and all the eigenvalues are non-negative. These come up in a variety of applications, right? If you want to approximate a covariance matrix, or as I mentioned, a kernel matrix, Laplacians are also PSD. Is there an n in z of A time lower bound for low-rank approximation of PSD matrices? Well, it turns out that the answer is no, and the main result of these two works culminates in the following, which is that given an n by n PSD matrix A, you only need to read n times k over epsilon entries of A. And there's an algorithm, having read those entries, the total running time of the algorithm is n times k over epsilon to the omega minus 1. So omega is the matrix multiplication exponent. In practice, it's 3. This would be n times k over epsilon squared. In theory, it's conjectured that omega is 2, and then this would just be linear. It would be up to a constant factor, the same as the number of entries that you're reading in A. So in this very small amount of time, it is possible to output a rank k matrix A prime as we wanted. It's a randomized algorithm, which with high probability satisfies that the Frobenius norm of A minus A prime is at most 1 plus epsilon times the optimal cost. So it gets this relative error guarantee that we desire. And it is possible to show a lower bound here by adapting, by sort of planting large entries, but keeping a PSD matrix. You can show a lower bound of n times k over epsilon entries. So this is optimal. Okay, so let me just describe how we get this result. And the first thing to observe is that the lower bound that I said earlier of like, please find the infinity for me, this matrix is not PSD. Now, why is it not PSD? Well, here it's not even symmetric, but the main point here is you can't hide large off-diagonal elements in a PSD matrix. How can you formally state that? Well, if I have a PSD matrix A, then it can be written as B times B transpose, or B is the square root matrix. And so if I want to look at the ijth entry of my PSD matrix, well, it's just the dot product of the ith row of B and the jth column of B transpose, also called the jth row of B. So just the dot product of Bi and Bj, which by Cauchy-Schwarz is at most the Euclidean norm of Bi times the Euclidean norm of Bj, which by arithmetic mean geometric mean inequality is at most the squared norm of Bi plus the squared norm of Bj over 2. And the point is the squared norm of Bi, well, that's exactly the ith diagonal element of A. And the squared norm of Bj, that's the jth diagonal element of A. So if I look at some off-diagonal entry, its value is at most the average of the 2 diagonal entries that it corresponds to. So in particular, if I had a large off-diagonal entry that's trying to spoil my low-rank approximation algorithm, one of those 2 corresponding diagonal entries must be large. And so I would detect that just by reading the diagonal, which is only order n queries. So the diagonal encodes a lot of information for PSD matrices, and it allows you to skirt this lower bound.
Is the same true if I throw an absolute value in?
If what?
Absolute value.
Absolute value of yeah.
Is a negative infinity a problem?
No, it's not a problem. Like the absolute value of this entry is this, which is less than this, which is less than this, right?
Thank you.
Yeah. Any other questions? Okay. There's a question in the chat box. Yeah, you can just argue directly by principal minors. Sure, yeah. But I want to say this as a sort of highlight here that the diagonal is going to play a very important role for our algorithms. And here is some further intuition about this PSD matrix. You can think of it as someone providing you a table lookup for the square root B of that matrix, right? So suppose you wanted to run some algorithm on the square root matrix B, and your algorithm involved a lot of dot products between rows of B. Well, every time you need a dot product, you don't go off and do expensive computation to compute the dot product. You just read the single entry in A. So you use A as a lookup table for solving problems about B. And this is great, as I said, if you have an algorithm for B that just needs dot products between its rows. And in fact, there are lots of low-rank approximation algorithms that have this form. For example, one such algorithm is to sample a row of B proportional to its squared norm. Now you have that row. And now you want to sample another row of B proportional to its distance to the row that you've already sampled? Well, you just need the dot product of that new row with the row that you've already selected. Now you have 2 rows. And now you want to sample another row proportional now to its distance to the span of the first 2 rows you've already sampled. Well, you just need dot products of all the rows to these 2 new rows, and so on. This is called adaptive sampling. It's a common low-rank approximation algorithm, but it can be implemented with roughly n times k dot products, which means that you just need to read nk entries of A. You don't have to do this expensive computation. Okay, so the point here is you can implement a low-rank approximation algorithm for B using A, and you might think, well, that's great, right? Because the best this is the square root matrix. So the best low-rank approximation to B, if I had 0 error, it has the same span. The right factor is the same as that for A, and so I would get a low-rank approximation to A. The end. I'm done. The problem is the approximation doesn't translate over so easily. So if you get an approximate low-rank approximation to B, it doesn't necessarily give a good low-rank approximation to A itself. Now, if you set this accuracy parameter epsilon small enough, as we just said, it'll eventually be a good low-rank approximation to A. But it turns out that you need to set epsilon for low-rank approximation to B to be super tiny to get a low-rank approximation for A. If you do it naively, this epsilon even needs to depend on the top k singular eigenvalues of A, or singular values of A. They're the same here, and then you get a running time which is kind of uninterpretable. It depends on properties of A. It could be arbitrarily large. If you do it carefully, you can set epsilon to be roughly 1 over root n. And then if you get a 1 over root n approximation to B, you get a constant approximation to A. But the problem is that these algorithms for B, the number of entries that they require reading in A scales roughly as nk over epsilon. So if I have to set epsilon to be 1 over root n, this is not good enough for us. This would give us an algorithm that reads roughly n to the 3/2 entries. There is an algorithm that does that, based on this, what I'm saying, but that's not what we want. We want an algorithm that only reads order n entries and spends roughly order n time. Okay, but this intuition about table lookups is very useful. Okay, and one better way of getting a low-rank approximation is what's called ridge leverage score sampling. Okay, so let me just say what ridge leverage scores are. And to do that, let me just remind you what leverage scores are. So if you have an n by d matrix, let's say n is greater or equal to d, and I can take an orthonormal basis for the column span of that matrix. Let's call it U. Then the ith leverage score is just the ith squared row norm of U. Okay, so the ith squared row norm. The squared column norms are all 1. It's an orthonormal basis, but the squared row norms can be anything between 0 and 1, and they're called the leverage scores. I mean, they still add up to D, but you can't really say anything a priori about one particular leverage score. So these are called the leverage scores, and these measure the importance of a coordinate I, because another characterization of leverage scores is this equals the supremum over all vectors y in the column span of U, so y that can be written as ux, of the squared ith coordinate of y divided by the squared length of y. Okay, so this kind of says, how much can the ith coordinate influence the overall length? So it would make sense to sample coordinates with high leverage if you want to preserve properties about your subspace. Those are standard leverage scores. And what I'm talking about here are ridge leverage scores. What these are as follows. The ith ridge leverage score of A Well, it's the evaluation of this quadratic form, which is a PSD matrix. You're evaluating it at the ith row of A. So multiply on the left by AI transpose, on the right by AI. What is this matrix in the middle, this quadratic form that you're evaluating? Well, if I didn't have this term here, it would just be A transpose inverse. Well, this would just turn out to be the standard leverage score. So, if you write down the SVD of A and you cancel all the orthonormal factors, the singular values cancel, you'll just get the I squared norm of U, squared row norm. And okay, so then what happens when I put this term in here, which you can think of as a regularization term? Well, what it's going to do is it's going to add this value to the singular values of AA transpose. And so what it's kind of doing is, the large singular values, they don't really get affected by adding this value. I mean, they're so large that they matter for a low rank approximation. And I'm adding this term that, is within my error of a low rank approximation divided by K. So these top K terms, K singular values, they're not really affected by adding this. And the much smaller singular values, well, they all get increased by this amount. So it's a much smoother spectrum at this point. Okay, so this is just the this quadratic form for ridge leverage scores. And what is known about sampling rows of your matrix A by these ridge leverage scores independently? Well, what's known is the following. It's a very cool property. If you sample K log K over epsilon squared, let's say columns of A, according to the ridge leverage scores, okay, this distribution on columns, and then you just simply output the top K singular vectors of your sample, then boom, you're done. Those top K singular vectors of your sample form a good n by K left factor of a low rank approximation. And that's it. So these are great sampling probabilities for low rank approximation. And okay, so one issue in our setting is, well, we want a low rank approximation for this matrix A, this PSD matrix we're given. And we don't know these ridge leverage scores. And the whole point is to try to do things quickly. And it's not clear how to compute the ridge leverage scores of A without reading all the entries of A, which would then defeat the whole purpose of this talk. Okay, so what are we going to do? Well, now we're going to go back to this table lookup intuition. What if we could somehow relate the ridge leverage scores of A to the ridge leverage scores of the square root matrix B? It turns out that you can. You can show that just using this definition, this quadratic form that I gave you, you can show that the ith ridge leverage score of A it's at most root n over root k times the ith leverage score of B, ith ridge leverage score. And the proof doesn't use anything fancy, right? You just use that A equals BB transpose, and you use the definition, okay? And you do some algebraic manipulation. Okay, well, what does that buy us? Doesn't seem like that's very useful. Well, it turns out that there are algorithms for computing the ridge leverage scores of B that just involve a small number of dot products between rows of B. So going back to this table lookup intuition, we can use A as a table lookup for running one of those algorithms. There's a nice algorithm of Musco and Musco, which shows that you can compute all the ridge leverage scores of B reading only order n k entries of A, your table lookup input. Okay, so great. So we have the ridge leverage scores of B, and now we have this relationship that constrains the ridge leverage scores of A in terms of those. And by standard sampling guarantees, if I don't have the exact sampling probability, but I have some upper bound on it, then all I have to do is oversample by that upper bound. And so by standard sampling guarantees, if we sample column I of A, instead of according to the ridge leverage score of A, which we'd like to, but we sample by the ridge leverage score of B, so we form this matrix C, which stands for columns, equals A times T. T is just a sampling matrix, okay? So it's going to select columns of A and then just rescale them to preserve expectations. But instead of just sampling by the ridge leverage scores of B, if you oversample by a root n over root k factor, then this simulates sampling according to the ridge leverage scores of A. And so the same thing works, just take the top k space of your sample and you're done. And this leads to an n to the 3/2 poly k over epsilon time algorithm. So we haven't, really made so much progress so far. We saw, another way of getting a similar subquadratic time algorithm. But what do you think we should do now that we've sampled columns? Instead of reading all of those columns, what could we hope to do to get an even better algorithm? Well, what if we try to sample rows now? So we've, kind of squashed A down, its columns down to a small number of columns. Can we also simultaneously squash down the number of rows? Well, this is a little bit more difficult. It's not so easy to sample rows. Since, what did we need? Well, we needed the ridge leverage scores of A, and we got them by, finding the ridge leverage scores of B and relating them to A. Now we need to sample according to ridge leverage scores of our sampled set of columns, C, which is equal to A times T, as I said. But we no longer have a table lookup for this matrix, or there's no notion of a square root of this matrix and so on. It's not clear how to do this quickly. Nevertheless, you can show that if you still sample root n poly k over epsilon rows of this, small set of columns AT, still using the same distribution as before, the ridge leverage scores of A, and then forming this now tiny root n by root n roughly matrix, which I'm calling SAT. S is a sampling matrix for rows, then this still works. I'm not going to prove it to you, but intuitively AT has some strong properties. It well approximates A in many senses, which kind of means that the ridge leverage scores of A are good substitutes for the leverage scores of A times T. Okay, I won't prove it to you, but using the ridge leverage scores of A again, which we have by finding the ridge leverage scores of B and using a root n overestimate, we can still get good sampling probabilities to form this tiny matrix SAT. And now we're in fantastic shape. We've sampled columns, we have root n columns, we sampled rows, we have root n rows. We have this tiny matrix SAT, and we can just afford to read all the entries at this point. Read all the entries of the tiny matrix, and we compute an approximate SVD of this matrix using whatever favorite algorithm we want. For example, the N and Z of number of non-zero entries of a matrix time algorithm I mentioned earlier. Okay, let me just, there are several steps to this algorithm, so let me just recap it in a picture here. What do we do here? Well, we started with this n by n PSD matrix A. We sampled a subset of columns C, so that corresponds to A times a sampling matrix T, roughly root n columns. And then we further sampled rows of that matrix, and we got SAT. And now we have this really tiny root n by root n matrix. And we ran our favorite SVD algorithm, and we found k directions, which is a k by root n roughly matrix V, which is a good right factor for an SVD for this matrix SAT. But what good is this matrix V? I mean, it doesn't even have the right dimensions. How are we going to use it to extract what we ultimately want, which is a good right factor of A as well as a good left factor of A, U? Well, the idea is we're just going to go backwards. Okay, so how do you go backwards more precisely? Well, we're just going to go backwards through a sequence of regression problems. Okay, so what does that mean? We have this V for this small matrix SAT. We're going to first go backwards to this set of columns C. So we're going to set up a regression like min over left factors u. This would be like a nice k-dimensional space for C, u, of u times v, we know v, minus C, Frobenius norm. Now we can't even write down this regression problem because we don't want to read all the entries of C. You know, sort of a really nice thing so far is these sampling matrices didn't have to read the entries of C. Well, we have V in our hand, so what we can do is leverage score sampling again. This is our favorite sublinear time algorithm. So let R be a sampling matrix from the column leverage scores of V, which we know, right? So, you know, there's a bunch of column leverage scores here. We're going to compute them all. And let's sample by them. So we right multiply V by our sampling matrix R, and we right multiply C by our sampling matrix R. But after having done that, CR is now this like really tiny subset of columns of C. It's certainly not root n columns. The number of leverage score samples you need is again like roughly K or K over epsilon. And so now I can afford to read this set here, CR. And I know V, so I know VR. And now I can find this nice rank K factor that's, you know, sitting inside of CR. Fantastic. This rank K factor U, it's an n by K factor, turns out to be a good left factor for A as well. Okay, but I still don't have my right factor for A. Well, what should I do? I should just do it again. Let's go back with regression again. Now we're setting up the problem. We know U, but we want a V. This V is now the right factor for A, not for this tiny matrix anymore. And we set up this regression problem. We can't write down this regression problem, but we can sample according to the leverage scores, the row leverage scores of U. We have to make roughly K over epsilon samples, and we set up this sampled problem. But all that requires is accessing K over epsilon rows of A. Again, there are some K over epsilon rows of A that we have to read here. Now we've set up this small regression problem, and we can solve for V, which sits inside of those K over epsilon rows. It's a good right factor. We're done. Okay, so we kind of went back through a sequence of regressions that all just involve sampling based on probabilities that were defined by matrices that we knew, that we either accumulated by going backwards or found from this very tiny matrix in the beginning. And that's it. So we got U. It involved reading K over epsilon entries of C, you know, which are themselves columns of A. And we also had to solve for V, which read K over epsilon rows of A. And so this is totally within our budget, NK over epsilon queries. Are there any questions? Okay. So that was the algorithm, the initial algorithm in the first paper with Musco. And the follow-up work, well, we really wanted to get optimal poly K over epsilon factors. I mean, you know, if epsilon is fairly small, like, you know, 1 over n to the 1/3 or something, the algorithm's not so good. If you analyze the algorithm carefully that I just described, you have to sample root n K over epsilon squared columns, then root n K over epsilon cubed rows, you know, whatever. In total, this is nk over epsilon to the 5th entries, which is, you know, not good if epsilon is small, as I said. So, you know, one thing is if you look at this analysis, both of these column and row sampling procedures, they preserve lots of stuff. Like they're very strong. If you're familiar with core sets, they preserve all rank K projections. And this is totally unnecessary for solving this low rank approximation problem. You know, so one of the sort of main ideas that we had, a starting point here was, wouldn't it be nice if we could look at this bound and replace epsilon with a constant and replace the rank parameter K with K over epsilon? Okay, this is just pattern matching. There's no reason for this. But this goes away and you get nk over epsilon, which is exactly the time we're looking for. But it turns out this is actually exactly what we do as well. Okay, so we do show how to adapt this previous algorithm by setting epsilon to a constant and k to be k over epsilon. Now, what does this mean? You can't just set k to be something else. You want a rank k approximation at the end. By the way, this does match this nk over epsilon lower bound I mentioned earlier. Okay, so why should this work? Well, what do you even get when you sample a subset C of columns? Let's just look at this first stage of the algorithm. It's going to sample a subset C of columns with these really horrible parameters. Epsilon is set to a constant. K, well, we gain something there. K is now k over epsilon. The guarantee that you get is what's here. Yeah, it's a bit of a mouthful, but let me just say it. It says that for all rank k over epsilon projections P, you have that if you look at the distance from C to P, what does that even mean? It means the squared operator norm, max singular value, of C minus P times C. Well, it's not so far from the squared operator norm of A minus P times A. Now, first the dimensions make sense. C has the same number of rows as A, though C has many fewer columns. So, this is some kind of compression of A that preserves the cost of all rank k over epsilon projections. It preserves it in a very weird sense. So multiplicatively, it preserves it up to a constant factor. And then there's this additive error as well, which depends on the Frobenius norm of the tail of A after removing the top k over epsilon entries. And nicely, there's a leading factor of epsilon over k here. But you look at this and it's a mess and it's kind of horrible. There's a constant factor approximation here. How in the world are we going to get a 1 plus epsilon approximation from this? Well, the nice thing is we're not going to just do this simple algorithm of sampling and then finding the top k directions in the sample. We're going to find a very special projection, which was used in earlier work with Clarkson, which satisfies what's called the SF property. SF stands for spectral Frobenius. It's a mixed guarantee. So P is a rank k over epsilon projection, just like what this mysterious guarantee accommodates. What it says is that C minus PC, its squared operator norm, is at most epsilon over k times the squared Frobenius norm of, in fact, you can put C minus CK here. And that's why it's a mixed spectral Frobenius guarantee, because it relates spectral error, the spectral error of using this projection, to the Frobenius norm of the best rank k approximation. But it turns out for this C that we're looking at, this is will always be theta of the squared tail Frobenius norm of A. Okay, so I can actually put what was here on the slide. If I have this SF property, it turns out that this horrible guarantee is enough to solve the whole problem. Why is that? Well, let's just look at this left inequality here. So, forget about what's going on the right. Well, suppose I take this P that has this SF property and just plug it in here. I move this to the other side, this Frobenius norm loss. I use my nice SF property guarantee. And, I divide by 0.9 on both sides, whatever. I get that P also has the spectral Frobenius property for A. And why is that useful? Well, it turns out if you have the spectral Frobenius norm property of a matrix, then there is a good rank K solution in its span. Namely, you can show that A minus P times the best rank K approximation to A times P, that squared Frobenius norm is at most 1 plus epsilon times the optimal cost. This is a rank K matrix. It lives inside of the row and column span of P. And so once I have this P and I have this property, you can prove this just by expanding things using trace and using this SF property. Then you can left and right leverage score sample from P, which reduce this to a super tiny problem and solve for this unknown intermediate matrix. And this guarantees you're going to get a 1 plus epsilon approximation. So what we've observed is that this problem, it really just reduces to finding this P that has the SF property for this set of columns C. Okay, so this horrible guarantee is sufficient, and now we just have to find this matrix P. And everything else is sublinear time, and we're done. So yeah, so I've just repeated what I said on the previous slide. All we need is for this rank K over epsilon projection P to have this SF property. Nothing new here. Okay, well, how can we do it? Well, we're squashing down to this really tiny matrix. We're again ridge leverage score sampling on the left and right. All is the same as before, except we reparameterize things. We replace epsilon with a constant and K with K over epsilon. But the same structure of the algorithm. So if you're to implement this, it would be the same code with different parameters. Now you can find once you have this tiny matrix, now you have to find projection Q with this SF property. That can be done using existing work from Cohen et al. But this Q is no good for us. It's on the right, not on the left. And more specifically, it has super tiny dimensions, and it should be because you're looking at a super tiny matrix. So there's no way that this can be, have the SF property for C. It doesn't even have n dimensions. But if you have a good matrix on the right with the SF property, what do you think you should do? What have we been doing so many times in this talk? Well, you should set up a regression problem. So let's set up a regression problem where this is the matrix you have on the right and try to find a good matrix on the left. This is a somewhat unusual regression problem in that you're minimizing operator norm. So you're trying to find some unknown rank K over epsilon W that minimizes the operator norm of the difference. And we call this spectral regression. And it's not so clear that if you just sample from the leverage scores of Q, which is what we've been doing to go back up to bigger matrices before, that it would even work for this much stronger guarantee. Like maybe you need some properties of C and you can't afford to read C and the whole algorithm breaks. But it turns out that you can still just sample from the leverage scores of Q. And this is one of the technical contributions here that I don't have time to get into. But it turns out you can solve this problem and just use the projection onto your solution W to spectral regression as your projection. And surprisingly, just sampling from the leverage scores of Q works. This proof, what it does is it utilizes a theorem of Rudolphson inversion in. If you have a matrix and you sample some of its rows uniformly at random, what is an upper bound on the operator norm of that sampled matrix? So Rudolphson inversion give nice bounds on that. We have to adapt it a bit. We have rectangular matrices. We don't have uniform sampling probabilities. Their bounds are not so good. They depend on the row norms of the matrix. We can get by all this just by having additional logarithmic factors. We can kind of bin our sampling probabilities into powers of 2. So on one of those bins, it looks uniform. We can bin the row norms into powers of 2, yada, yada, yada. We eventually reduce it to a logarithmic number of uniform sampling schemes, or polylogarithmic number. And then we can apply the result. Okay, so I'm sorry I don't have time to get into that, but it's a nice use of this in this context, in my opinion. And spectral regression is less studied from a sampling perspective. That is one of the technical contributions here. And that concludes the algorithm for PSD low-rank approximation. I only have a few slides left since I started a few minutes late. Let me just cover them. These are more.
Sorry, David, I think that we have to move on to the next speaker.
Okay. Oh, sorry. Okay. Then let me just say that these results apply to distance matrices as well. It's another sublinear time family of matrices. They're very related to PSD matrices. And then let me just conclude then. We gave optimal sublinear time algorithms for low rank approximation of PSD matrices and a related family of distance matrices. A key idea was to use a PSD matrix as a lookup table for algorithms on the square root matrix. Another key idea for getting optimal bounds was to use this spectral Frobenius norm property that I talked about. And finally, the open questions are clear. Can you get low rank approximation of many other structured matrices using sampling techniques? Maybe these are helpful for that. That's all. Thanks very much.